All right, so this is, I guess, part two of driving Kepler's laws from the universal law of gravitation. So, of course, uh, Newton's law of gravitation was that force, which of course is ma, is minus gmm over r squared, r hat. And we saw this was useful to go ahead and write the r hat in terms of r. So minus gm m over r cubed r. Right. And then we saw just from the fact that this is in the A is in the same direction as R, that gives you Newton's second or Kepler's second law. We're actually going to get Kepler's second law again in the process of getting Kepler's first law. But anyway, last time all we had to do was say, okay, well, since R cross A is 0, that gives R cross V is constant, which is basically Kepler's second law. All right, well, let me say one more thing about this. You may recognize R cross V if you've taken physics, namely M times R cross V is angular momentum. So another way to get this, if you already have a little bit of vested physics in there, is that, the reason Kepler's second law is true is the conservation of angular momentum. But that's actually proving the conservation of angular momentum is pretty tough, so that's why we didn't do it that way. But we're actually going to get Kepler's second law again in the process of getting the first law. So to get the first law, we need to remember what do position, velocity, and acceleration look like in polar coordinates. So position's easy. R is just R, and then UR. So remember my polar coordinate system, my level curves look like circles. So UR is my unit vector. So if I'm at a point, UR is the unit vector in the direction of the radius. And U theta is in the direction of the angle. So R is just UR, that's no big deal. V is just, it's early in the morning, I'm having to think. So it's R dot UR plus R theta dot U theta. We're actually not going to need that one. The one we will need, though, is acceleration, which is our second derivative. And these derivatives are all with respect to time, which hopefully is sort of obvious, but R2 plus 2R dot theta dot U theta. Okay, so let's redo just really quickly the second law. Well, all we needed for the second law we saw last time was that this U theta component is 0. And the way we would do that in this notation, well, we have R theta double dot plus 2R dot theta dot is 0. Well, when I see this R and this 2R dot, I kind of think, well, R squared should somehow come to play. So if I multiply this whole equation by R squared plus 2R dot theta dot, multiply it all by R, so I get an R squared. The reason I do that is because now this side becomes d dt of R squared theta dot, right? Because if I took the derivative of this, leave the R squared alone, take derivative of theta, so R squared theta double dot, and then leave the theta dot alone, take the derivative of the R squared, derivative of R squared is 2R, and then times the derivative of R, so 2R R dot. So this says that R squared theta dot is constant. And of course, going back to the angular momentum thing, I'm going to go ahead and use notation for angular momentum just because I need a letter, and it makes sense to use one that's used in physics. So if I multiply this by mass, it's still constant. So another way to say this is that, well, mr squared theta dot is L. This is angular momentum. So this all turns into conservation of angular momentum. And if you wanted to write the second law, if you remember last time, we just had this would have been 1/2. We didn't have the mass in there, so that would be the second law. But we're not going to need that. We're just going to need this mr squared theta dot equals L. Okay. So now, so that was kind of just redoing what we did last time, but it's a little bit more complicated because we're using this polar coordinates and the equations of motion in polar instead of just using simple vector stuff. So now to get to the next part, we're going to use Newton's law of gravitation, and we're going to look at the radial component of acceleration. All right, so we know that, again, on one hand, ma equals minus gm over r cubed r, right? So I don't guess I need r. I could have just left this r squared. So let's do that. And this, what I was calling r hat is now ur. Okay. Well, the m's cancel. That's easy. And then a, if I go up here, just read it off. This is r double dot minus r theta dot squared times ur hat. So get rid of those. So the equation I need to solve is r double dot minus r theta dot squared is gm over r squared minus. Okay. Well, the first thing I want to do is, at least temporarily, I'm going to get rid of theta, and I'm going to do that with conservation of angular momentum, because we had m r squared theta dot is L. So theta dot is L over m r squared. So I can plug that back in here. And so I'll have r double dot minus, well, when I square this, I'll get L squared over m squared. And then I'll have r to the fourth, but then I've got an r here, so altogether I'll have r cubed minus gm over r squared. So that's the equation I need to solve. And if you've taken differential equations class, it might be a little surprising when you can solve this. It looks really not like anything you studied in differential equations. So, but if you think about the answer that Newton knew he was probably going to have, so remember, Kepler had already empirically figured out what the answer should be. It should be an ellipse, which in polar coordinates looks like a over 1 plus epsilon cosine theta minus theta 0 or whatever. Right? So if we know that's where we're headed, that kind of suggests for us to do two things. Right now, this second derivative is with respect to time. So knowing where I'm going, I would kind of like to change that to theta. So I want to do two things. First thing I want to do is change the independent variable from t to theta. And then the other thing is, well, if I look at this formula, it's not a terribly complicated function, but it's not terribly simple either. On the other hand, if I did 1 over r, 1 over r would be 1 over a plus epsilon over a cosine theta, right? So if I look at that, those are the sorts of solutions I'm really used to getting when I took my differential equations class. So that at least suggests it might be a good idea to change my dependent variable as well. So I'm going to change the dependent variable from R to, and call it whatever, I guess, say maybe, we already used V, so how about Z is 1 over R. All right. Okay. Well, let's talk about changing the independent variable first. Normally that's a little tricky to do, but actually, because of this conservation of angular momentum, we can do this part really, really easily. It's actually, that's almost our change of variable right there. So we have d theta dt is L over m r squared, which, keeping in mind I'm going to change r to z, this would be L over m times z squared, right? So if I just, I'm going to divide both sides by d theta. I mean, that's really a chain rule thing, but I mean, that's why Leibniz invented this notation, was so that you could kind of do screwball things like this, and it really works. So my change of variable formula is d dt is L over m z squared dd theta. So if I want r double dot, well, that's d dt of d dt of r. Let's just take the inside for now. So I want d dt of 1 over z, right? Well, that's L over mz squared dd theta of 1 over z. And now we already see some magic happening. So when we take this derivative of 1 over z is negative z to the negative 2, and then dz d theta. And so, yeah, the z squared cancels the z of the minus 2. So that's already pretty awesome. Makes our life a lot easier. So I've got L over m dz d theta. And now go one more time. I need to hit that with d dt again. So L over m z squared dd theta. Again, this is just dt, or d dt. And then I'll need to hit this guy, which is L over m dz d theta. L over m is a constant, pull it out. So I've got L squared over m squared z squared d squared z d theta squared. This is my r double dot, now written in terms of z and theta instead of in terms of r and t. All right, so I'm just going to take this and plug it back into my equation I had up here, which I have already forgotten. So, okay, r double dot, I'll write the rest of it here in a second. So the r double dot is L squared over m squared, z squared, dz d theta squared, and then I had minus, what did I have? Minus L squared over m squared r cubed, L squared over m squared. R cubed is now, r cubed on the bottom is the same thing as z cubed on the top. And then same thing, minus gm over r squared. That's minus gm, and then over r squared is the same thing as z squared. And so happily I can cancel a z squared out of the whole thing. And let me go ahead and clear these coefficients too. So I'm going to multiply the whole thing by m squared L squared, or sorry, m squared over L squared z squared. So that gives me d squared z d theta squared minus z, right? equals minus gm m squared over L squared. If I did all my algebra right. Okay. Now I have a minus sign where I feel like I really need a plus. Let me go back and double check things. I would like that to be a plus sign right there. So let me just double check, make sure I didn't make any mistakes. That's where I lost my minus. I had a minus here that I lost. So there's minus, there's minus. So this should actually be minus. So if I multiply the whole thing by minus, that makes that plus, and that plus. Okay, that looks a lot better. Because now I recognize this as being a very, very simple equation. This side, the solution is cosine, right? So if you remember your differential equations class, which I know many of you taking Cal 3 have not had differential equations, but basically if you want to solve something like this, you start off, you solve the equation with that side 0. And this equation is really easy. It's just z is some a cosine theta minus theta naught. So because if I take two derivatives of the cosine, then I get cosine with a minus, and so minus cosine and cosine add up to 0. Once I have the solution for one side 0, all I need to do is find any solution for the actual side I have. And then if I add that to this one, so this is called the homogeneous solution, I need a particular solution. If I find any solution for this equation, I add to that, that gives me the general solution. Well, a simple solution for this equation, this side's constant. So I could just say my particular solution is gm squared over L squared, right? So my general solution to this equation I started with is the particular, then plus the homogeneous. So I get z in general looks something like gmm squared over L squared plus a cosine theta minus theta naught. And so u, which is what I actually cared about, u is 1 over gm squared over L squared plus a cosine theta minus theta naught. Boom. So sure enough, this is conic section. So exactly which type of conic section will depend on A. So the eccentricity would be A divided by gm squared times L squared. So if this is less than 1, sure enough, we get an ellipse. If A was big, this could equal 1, we would get a parabola. So the guy would never come back. You'd do something like that. Or if it's greater than 1, we could get a hyperbola. So a parabola is kind of, it comes in and goes back out on the same direction. Hyperbola would be it comes in and goes out 2 different directions. So those are possible. But if we're actually talking about an orbit, well, an orbit has to repeat itself. So the only one that repeats itself is the ellipse. If it was on a hyperbola or parabola, that would mean it just passed really close. And I mean, like, say we had a really big, massive body and something coming along on just its merry way. Well, it's going like this. The massive body could curve it, but not enough to actually make it go into orbit. That would be the hyperbola version. If we're talking about planetary orbits, then, well, yeah, they would have to be ellipses. So anyway, so that's the first law, and then that's kind of the hardest one. And then in the next one, we'll use this and figure out how to get the third law for general orbits, not just for circles. So if you remember at the beginning, we started out getting Newton's law by assuming Kepler's third law for circles. And Anyway, in the next video, we'll show how we can use Newton's law to get Kepler's third law in general.